Hello everybody and welcome to Capacitors lesson 4. In the last video we were looking at the capacitor discharge equation, and the main one that we had was Q is equal to Q naught E to the minus T over RC. Now of course we showed that there are a couple of different versions of that because charge and current are proportional to each other. We can say that I is equal to I naught E to the minus T over RC, and we can also say that V, that's obviously the potential difference across the capacitor, is V naught E to the minus T over RC as well. Now in this video what I want to do is I want to delve a little bit more into these equations, and I really want to focus on the exponential decay part of this, so the E to the minus T over RC section, and make sure that we understand exactly how that works, what it means, and obviously from a mathematical point of view we understand how to deal with it as well. Firstly then, looking at this equation, I want to draw out what's known as the time constant, and hopefully we'll see why it's called the time constant in a moment. Now firstly I want you to have a look at this bit here. Okay, so it's whatever E is raised to, so we've here got T over RC. Now one of the mathematical rules that we have to follow is that whenever we raise a number to a power, that power must overall be dimensionless. So in other words, what we're saying is that when we do T and divide it by R times C, so the resistance in the circuit multiplied by the capacitance of the capacitor, that overall that term must be dimensionless, it must have no unit. But of course we know that the unit on the top of this fraction for time is seconds, and therefore overall when we multiply R by C, that overall must also have the unit of seconds, so that everything cancels out and that term T over RC becomes dimensionless. But of course what that tells us then is that the unit of RC is in seconds. Okay, so it's got the same unit as time, and therefore this term here, this R times C, is known as you can see at the top of the slide, the time constant. Now of course we can consider it to be a constant because in a given circuit the resistance will be fixed and the capacitance of the capacitor will be fixed as well, and therefore those, at least for any given circuit, would be a constant. Now what I want you to do, what I'd like you to do, is just pause the video at this point and just with a scrap of paper or something like that, just quickly jot down and just show yourself using dimensional analysis that in fact R times C, so resistance times capacitance, does, when you boil it back down into its SI base units, does give you overall seconds. So like I said, just pause the video, give that a go, and I'll go through it in a moment's time. So then, to show that that is the case, what we're going to do is we're going to have a look at, obviously, we use a square bracket to say the unit of, so the unit of R times C. Now I'm going to use two equations here. Firstly, I'm going to use V is equal to IR, so that's obviously Ohm's law, and therefore we know that R is equal to V over I. And then secondly, we're going to use the definition of capacitance from before. C is equal to Q over V. So therefore, when we do the units, so firstly, let's do R. So the unit of potential difference divided by the unit of current, and then multiplied by the capacitance. Well, we're just going to do there the unit of charge divided by the unit of potential difference. Now what you can see when we multiply these two terms together is we've got the potential difference on the top of one and on the bottom of the other. So obviously if we're doing this from an algebra point of view, we cancel the v's out, but obviously what that means is we can cancel the units out as well. And what we're then left with is that the units of R times C is equal to the unit of Q, unit of charge, divided by the unit of current. But of course, remember the definition of current in the first place. We know that I is delta Q by delta T, or in other words, and quite often, especially back at GCSE, you will have used the equation Q is equal to IT. And therefore, when we substitute that in for Q, we've got the unit of current multiplied by the unit of time divided by the unit of current, and once again we've got current on the top and on the bottom, and what we're left with is the unit of the time constant has to be the same as the unit of time, and therefore we end up with seconds. Let's have a look then at what the time constant means for the equation and how we can use it. So let's just bring the equation back. So Q is equal to Q naught E to the minus T over RC. Now what we can do is let's just have a look at what happens after we've had one of those time periods. So after or when T is equal to that time constant R times C, let's have a look at what happens to the equation. Well, we've still got Q is equal to Q naught, and we've now got E to the minus RC. Okay, so we've set T is equal to RC. So let me use a different colour there to show you that substitution. So we've got RC divided by the original R times C, the time constant itself in the equation. Well, of course, that bit, RC over RC, they cancel each other out, and we're left with Q is equal to Q naught E to the minus 1. Well, of course, whenever we do anything to the power of minus 1, that just means that we're dividing by it. So we can also write that as Q is equal to Q naught divided by E. Now remember that E itself, Euler's number, it is just a number and it has a value. We know that E is 2.7182818, etc. So when we bring that back onto our graph, so let's take the graph as a graph of Q against T, and let's say that this value here, obviously our initial value by definition is Q naught. Well, if we again by definition start at T is equal to 0, well, once we've had one time constant, if we trace up and we trace across, then we've reduced the charge from Q naught now to Q naught over E. Now when you do E to the minus 1, you do work that out as a number, or obviously 1 over E. That works out, and you can just very easily do that on your calculator, of course. 0.3678794, etc. Obviously we don't need that many significant figures, but what we're saying then is, so after one time constant we've come from Q naught down to Q naught over E, and when you have a look at the numbers, that works out as approximately 36.8% of Q naught, so it's just over a third of that original value. Now of course we can do the same and have a similar view of what happens after two time constants. So we can say after two time constants, and let's do a similar process, and some of you might already see where we're going to go with this. So Q is equal to Q naught E to the minus, well, let's do our substitution, 2RC divided by RC, and once again they end up cancelling each other out, and we're left with Q is equal to Q naught E to the minus 2. Now of course E to the minus 2, we could write that differently as Q naught over E squared. Now obviously bring that back over to the graph, and I'll do this in a different colour so we don't get too confused. So here would be 2RC on the graph, okay, and we've come across to, okay, this point here, which will be Q naught over E squared. Now obviously again, just putting E squared into your calculator isn't that difficult, because there's a button on your calculator which I'll show you in a minute is the easy way of getting E to the power of anything, but E to the power of minus 2, or obviously 1 over E squared, is equal to 0.1353. I won't go into all the significant figures there, but you're looking there at around about 13.5% of the initial value. Now of course we can take that idea one step further, we can come up with more of a generalisation. So let's just bring the equation back again, and I know that I'm using Q equals Q naught E to the minus T over RC, but obviously a lot of what I'm looking at right now will work equally well with I equals I naught E to the minus T over RC, or V equals V naught E to the minus T over RC, because of course we're applying all this to the E to the minus T over RC part. So if we now say, well, what happens when, or after, a time of t is equal to some number, and we'll call that x, multiplied by the time constant. And of course that x can be any number, it doesn't have to be an integer. I know that we were looking at obviously after one time constant, after two time constants on the last slide, but there's absolutely no reason why that has to be an integer at all. So let's plug that in and have a look. So we get Q is equal to Q naught E to the minus, let's do our substitution, so it's now x multiplied by the time constant as the substitution, divided by the time constant itself from the equation. Those two cancel each other out, and what we're left with is that Q is equal to Q naught E to the minus x, or of course you can write that as Q is equal to Q naught over E to the power of x. So sometimes it'll be easier, rather than going through the whole equation, it's just to calculate the time constant and to have a look how many time constants have elapsed, and then to use a much simpler, much more boiled down version of the equation of the Q naught E to the minus T over RC equation. But of course, once you've got the time constant and you've got that idea, you can apply it to any of the equations that have E to the minus T over RC in them. So let's just have a quick look at how we're going to get E as a number on our calculators. Now there are two different ways. One of them is going to be more useful to you, at least for this context, than the other way. Now the first way, which really actually is the less useful way for you at the moment, is to use this button, sort of bottom and centre, which obviously you use to give you your 10 to the power of something for standard form. But we also normally use to get pi as well. Now you'll notice that we've got pi above it in the gold sort of yellowy writing, and then we've got E in the reddy pink writing. Now in order to get pi, what we would do is we would first press shift, and then we would obviously press that button to get pi as a number. And you'll notice that they're colour coded. The lettering of shift is in that goldy yellow colour, and the lettering of pi is in that same colour as well. In order to get E then, well, instead we're going to press the alpha button, and then we'll press that button afterwards. And once again, you'll notice that alpha and E, at least the lettering, are in the same colour. So therefore the colour coding works. If you press alpha, then you press that button, you press the E button, but of course it's the 10 to the X button, and then obviously if you press equals after that, your calculator will give you the value for E, 2.71828, etc. So that's one way of getting E as a number, but as I said, to be honest, that's the least useful way for you. The other way of doing it, which at least in this context will be more useful, is to notice that you've also got E to the power there. Now, the advantage of using this button as opposed to the button at the bottom is that your calculator will immediately then give you the box in order to put your power into. So it's very similar to using this button here, using your X to the power button, but of course with that one you should have already specified what X is going to be. But if you just do Shift and then your natural log button, it will give you E to the power, and then you can put your power straight in. So if you just do Shift and then E to the power, which obviously comes from the natural log button, and then all you need to do is put your value for the power in there. And that's it done. If you were to use that button at the bottom, the standard form button at the bottom, you would have to go through a bigger process. You would have to do alpha and then E, and then you would have to press the power button, the X to the power button as well, in order to make that work. So using this second go, and what I've just marked on there in green, is going to be far more useful and far more efficient for you in order to get your exponentials, in order to do your calculations. Finally then, before we move on to have a look at a question for this video, I just want to have a quick note about exponential decreases. Now, in theory, and at least mathematically, a graph that is an exponential decrease will never get to zero. That's at least what the theory says. But of course in physics we don't necessarily like that, and what we tend to do is try to look if there's a point where we can say that it's become so close to zero, especially compared to the starting value, that we can just take it as zero. And of course, one of these main words that we hear flying around all the time in physics is negligible. So really we want to know, at least like I said, from a capacitor discharge point of view, is there a point where you can just say that that capacitor has got a negligible charge left on it? So again, once again, let's think about the equation. So Q is equal to Q naught E to the minus T over RC. And you remember back to what we said a couple of slides ago, that after one time constant, we're down to, so obviously this is Q naught. Let's make sure we label our axes as well. So there's charge and there's time. So after one time constant, we're down to Q naught over E. After two time constants, we're down to Q naught over E squared, etc. Now remember that Q naught over E was approximately 36.8% of the original Q naught. We also said that Q naught over E squared is about 13.5% of the initial value. Now we could, if we wanted to, we could keep on going and keep on going and keep on going, but what I want to do is I just want to quickly jump ahead. I want to say, well, what happens after 5 time constants? So after 5 times RC, we know that we've got Q0 over E to the power of 5. Well, at that point, and you might want to do that in your calculator as well, at that point we've got around about 0.67% of the original charge. Now, so after 5 time constants, we've gone from the initial charge, Q0, and we've come down to basically 2/3 of a percent of the original value. Now, as a very basic rule of thumb, and it is really just a rule of thumb, if we say that after 5 time constants, we've pretty much lost the vast majority of the charge on that capacitor, and at that point, especially if we go above 5 time constants, way above 5 time constants, I would definitely then call that charge remaining as negligible. So here is your question for this video. A 50 microfarad capacitor is charged to a potential difference of 6 volts. It is then discharged through a resistor of resistance R. And then part A, after 10 seconds, the charge has been reduced by 99 microcoulombs from its initial value of 300 microcoulombs. Calculate the resistance. And then for B, what's the current flowing through the resistor after 5 seconds? So as usual, pause the video at this point, go and have a go at that, go and work out your answer, and then come back and we'll go through that. So for part A then, we're going to use obviously the equation Q is equal to Q0 e to the minus t over RC. Now you'll notice, and just be careful here, the charge has reduced by 99 microcoulombs. So what it's saying is that from its initial value of 300 microcoulombs, so it's not saying that Q is 99, Q in fact is 300 minus 99, which is 201 microcoulombs. Okay. So for A, I'm going to divide both sides by Q0 first. So Q over Q0 is equal to E to the minus T over RC. Now the next stage is that I'm going to take the natural log of both sides. So what I end up now is natural log of Q over Q0 is equal to, and when you do natural log of E to the power of something, you're just left with the power, so that's minus T over RC. Now when we plug the numbers in then, so natural log of Q is 201 microcoulombs, so 201 times 10 to the minus 6 coulombs, if we really want to do it like that. Okay, so times 10 to the minus 6 divided by 300 times 10 to the minus 6. And obviously the reason why I've shown you that is just to show you that those 10 to the minus 6's cancel out. Now when you do that, what you're left with is minus 0.4, and then when you look at your calculator, 0.40047, etc. So even to 3 significant figures, that gives you an answer of minus 0.400. Now, of course, what we're left with there is just saying that minus 0.4 is equal to minus T over RC. Obviously, those minus signs cancel each other out straight away. If we multiply both sides by RC, we've got T is equal to 0.4 RC, or in other words, RC is equal to T divided by 0.4. Now the time we know from the question, and we can plug that in, is 10, and 10 divided by 0.4 gives us a time constant of 25 seconds. Now I'm aware that I haven't yet calculated what the resistance is, but this value, this RC of 25 seconds, is going to be useful for us in part B. Now, of course, to calculate finally the resistance, we're just going to do 25 divided by 50 microfarads, so 50 times 10 to the minus 6, and that gives us a final answer of 500 kiloohms. Now for part B, and this is where we get the real usefulness of having already worked out the time constant. 5 seconds is now just 0.2 times the time constant. It's a fifth of the time constant. And therefore for the current, we know that the current is now going to be I0 multiplied by E to the minus 0.2, or of course we could say that I is equal to I0 over E to the 0.2. When we take that a little bit further then, so the current is going to be, well of course I is V over R, so on the top we're going to have 6 volts, sorry, not multiplied by, divided by the resistance, which is 500 kiloohms, so 500,000 or 500 times 10 to the 3. Let's write it like that, 500 times 10 to the 3. Okay, and we're going to divide that by E to the 0.2, and what that gives us as a final answer is 9.82 microamps. So that's it for this video then. To summarise, the main thing we've looked at today is the time constant, and the time constant is just the R times C bit in the equation, where we've got Q is equal to Q0 E to the minus T over RC. So it's that bit there that is known as the time constant, and therefore has the unit of seconds as well. And remember that after any value x multiplied by the time constant, any equation that we have, so Q will be equal to Q0 over E to that power of x. Obviously we know as well that that works for current, so I is I0 over E to the power of x, or obviously potential difference as well, works in exactly the same way. Finally then, we looked at after how many time constants can we say that something's negligible, and therefore we said that after anything sort of, not necessarily approximately, but after anything greater than 5 time constants, most values are negligible. So that's it for this video then. As usual, many thanks for watching, and I hope you enjoyed that and got something useful out of that. And of course, I'll see you in the next video.